Decimals and percents. Here we go. Here we have some examples of decimal place names. If you start from the left, it's tenths, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions. What would be next? 100 millions, billions. So here we have a problem where to identify the place value of the 8. Now if we look starting from the left, we got dot 258. The 8 is in the thousands position, and somebody says, can we name the number 0.258? Can we say it? It's 258 thousandths. We're now to name the place for the 2. So we start on our left. Dot 72s, tenths, hundredths. And let's say the number is 0.72, 72 hundredths. Here we're to name the value of the 6. Well, if we take the first 6, dot 6, that's 6 tenths. That's easy. Let's do the last 6. So we got to think. Now it's tenths, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions. So that's the 6, 10 millions. And now we got to count right to left to say what's the number 6908086. So that would be 6,908,086 10 millions. These values might be a little easier. These are to the left of a decimal point. You can think of them as integers right now. And if we want to name, what's the place of the 3? We go 1's 10, so that's 32. What's the place of the 7? 1's 7. What's the place of the 4? Well, that's 4. That's 10 thousandths. And if we said the number, it's 46,979. What's the 0? That's in the hundredths place. And if we were to say the number, it's simply 99. And what's the 4? 4. 4 ones. What's the 0? So that's thousandths. Number of thousands. We don't have any. It's 0. So we would say that's 341. How to add decimal numbers. Now, we have 6.4. We don't say 6 and 4 tenths. When we talk in general, we just say 6.4, and we're adding to it 0.7. Notice I put a 0 in front of that dot. I just don't write 0.7, 0.7. So if you add the 4 and the 7, that's 11. And 6 and 0 is 6. We drop the first one, move the second one to the 6, and that's 7.1. That's tuples. We go to our right. 0.59 and 0.36. Add the 1s, add the 10s. So we have 9 and 6 is 15, and 5 and 3 is 8. And the 1 from the 15 goes to the 8, and that's 95. So 0.95 is the final answer. Now, you might have noticed I said you add the 9s, that's the 1s, the 10s, the hundreds, the thousands. That's general tuple language. It's actually, you're adding the hundredths, and then you're adding the tenths. Okay, we look at our example to the lower left. We have 72.48. We're adding to it 5.2. I have lined up the decimals. Okay, and that's the key. You got to line up the decimals when you're adding decimal numbers. So we got 8. It's a 0 there, but nobody writes it. And you got 4 and 2 is 6. 2 and 5 is 7, and a 7. We go to our example on the lower right. 1.2 plus 5.3 plus 4.7. Doesn't matter how many numbers you're adding. We've lined up the decimals. 2, 3, and 7. That's 12. Dot. I think I have 154. That's 10. We move the 2 down. The 1 gets added to the 10. That's 11. So that's a 1 and a 1. So 11.2. How to subtract decimal numbers. Our first example is relatively simple. You have 6.4 minus 3.2. You do digit by digit. So 4 minus 2 is 2. And 6 minus 3 is 3, so the answer is 3.2. We look at the next one. It's 19 minus 2.6. There's nothing above that 6 in the 2.6, but it's a 0. And you can think of subtraction as changing every sign and adding. So when we take 0 and a negative 6, you get negative 6. 9 and a negative 2 is 7, and you have a 1. Okay, we've got to get rid of that negative. You add 10, take away 1. So that would give us a 4, and 7 minus 1 is 6, and a 1. That's tuple subtraction. Now we go to the lower left. We've got 7.72 minus 3.85. I've lined up the decimals. So you have 2 and a negative 5. That's negative 3. You got 7 and a negative 8. That's negative 1. And a 7 and a negative 3 is 4. So we got a negative 1 and negative 3. You got to get rid of our negatives. So you add 10, take away 1 next door. And now you got negative 2, a red negative 1, and a black negative 1. So you add 10, take away 1 next door. So negative 3 and 10 is 7. You got negative 1, 10 is 8, and 4 and a negative 1 is 3. We look at our next example, lower right, we have 0.67 minus 0.294. So here we go again. What's above that 4? A 0. So you do 0 and a negative 4, that gives you negative 4. 7 and a negative 9 gives you negative 2. And 6 and a negative 2 gives you 4. And we have dot and 0. So got to get rid of the negatives. So over by the negative 4, we add 10, take away 1 next door. And then we say have a negative 2 and a negative 1. That's negative 3. So we add 10, take away 1. And then we do 10 and a negative 4, that's 6. And negative 2, negative 1. And a 10 is 7, and 4 and a negative 1 is 3, and we have a dot and a 0. So that's how to subtract decimal numbers using tuples. How to multiply decimal numbers. It might seem a little hard at first, but once you practice it, it's pretty easy. Now here's the method. We're going to multiply two numbers, and they have decimals in them. We're going to count the digits to the right of the decimal points. We get the number, the product. We go to the right, and then we count or go to the left that number of spaces and place the decimal point. So we take a very simple example to start with. 3.1 times 4. Now, 4 times 31 is 124. We have one digit to the right, 1. There's no digit to the right of 4. The decimal in 4 is after it, 4 dot, but there's no digits. So we start to the right of the 4 and come back one space, and that's 12.4 is our final answer. That's in red. Now we take the same kind of numbers, but we have different decimal points. We got 3.1 times 0.04. We're only interested in the digits to the right of the decimal point, and we can see the 1 and the 04 are the 3 digits. So now we need 31 times 4. Still 124. But we have 3 digits to the right. We start on our right of the 4. We count 3 spaces back. The final answer is 0.124. Okay, we take another problem, say 0.034 times 0.06. So how many digits are to the right? Well, with 0.034, there are 3, and with 0.06, there are 2, so there's a total of 5. So we got to do 34 times 6. 6 times 4 is 24. 6 times 3 is 18. I'm doing tuples here. I bring down the 4. I add the 2 to 18. I get 20. So the final answer is 204. I go to the right of 204 and count 5 spaces back. So I go 1, 2, 3. That's at the 2. Add a 0, put a dot, and then add a 0 in front of your dot. And so our final answer is 0.00204. Well, we take a simple problem, 0.7 times 0.2. It's actually 7 tenths times 2 tenths. And there are 2 digits to the right. Sometimes 2 is 14. Go to the right of 14, come back 2 places, and our answer is 0.14. So it's a very simple method, and it works on all decimal numbers. How to divide decimal numbers. Now, before we do this, we have to go back, way back. How did we learn our multiplication tables? We were using integers. So what we could do when we divide, we want to divide by integers. So the rules are we move the decimal in the divisor to the right to make it the smallest whole number, then move the decimal in the dividend, that's what we're going into, to the same number of spaces to the right. So if we look down below to the left, I have 4.8 divided by 0.08. 0.08 is the divisor, and we use long division. So we look immediately below 0.08, and you see the arrow. I have moved the decimal 2 places to the right, and that number is now 8. But whatever we do in the divisor, we do in the dividend. So I move that decimal. It's 4.8, and we put a 0, and there I have moved that 2 places. So our new division, equivalent division, is 8 into 480. So 8 doesn't go into 4, but it goes into 48 6 times even, and 8 goes into 0 times, so our answer is 60. Now we look at same numbers, but we change them ever slightly with the decimal. So we're going to divide 0.048 by 0.8. So if we look down below, 0.8 is going into 0.048. We're going to move the decimal 1 place to the right in the divisor. That's 8. And we move it 1 place in the dividend. So 0.048 becomes 0.48. Now, move that decimal immediately up. So we see below 8 is going into 0.48. 8 doesn't go into 4. That's 0 times. You got to start after that dot and put numbers. And then 8 goes into 48 6 times. And so our answer is 0.06. And we're going to write it as 0.06. Here we have 3 more divisions. We're dividing by integers. So 4.8 divided by 8. So we look at the long division immediately below on the left. 8 is going into 4.8. 8's an integer. There's nothing to move to the right. So you move that decimal in the dividend straight up. You ask yourself the question, does 8 go into 4? No. Does 8 go into 48? Yep, 6 times. So the answer is 0.6, but we will write it as 0.6. Look immediately below. Does 24 go into 0.48? It does. We move the dot straight up because 24 is an integer. Okay, and you ask yourself the question, does 24 go into 4? No. You have to put a 0 after the dot. You can't leave them blank. That's a 0. Does 24 go into 48? Yes, 2 times exactly. So our answer is 0.02, and we write it as we see below, 0.02. And we take another problem over to the right. 0.048 divided by 80. So we set it up in long division. 80 into 0.048. And move that dot straight up because 80 is an integer. The divisor is an integer. So does 80 go into 0? No, put a 0. Does 80 go into 0.4? No, that's our second 0. Does 80 go into 0.48? No, that's our third 0. Add a 0 to the 48, so it's 0.0480. Does 80 go into 480? Yes, 6 times to check our work. 6 times 0 is 0, and 6 times 8 is 48, and that's 480. So that's our answer, but we're going to write our answer as 0.0006. So we put zeros in front of our dots. A new division method. We're going to divide 5, which is in green, into the dividend, which is in blue, 826. So we're going to do digit by digit. So 5 goes into 8 one time. 1 times 5 is 5. We subtract, we get a 3. 5 doesn't go into 2, so we're not going to bother with it. You can bring it straight down. And 5 goes into 6 one time. 1 times 5 is 5. You subtract and you get a 1. So we got an initial subtraction of 321. And we have a 1 space 1. Those are quotient digits. Now we go, how many 5s go into 32? 6. 6 times 5 is 30. We subtract, we get a 2. 5 doesn't go into 1, bring the 1 down. And now we go, 5 goes into 21 4 times. It's going to be above the 1 in the 21. And that 4 is the third division. And that's above the 1 above the 6 in blue. And we have a remainder of 1. And so the quotient, those digits, 1, and then we have a 6, and then have a 1 and 4 in a column. That is a tuple, and we add them up. 1s, 10s, 100s, we get 165. So what does all this stuff mean? It means that if you take 5, the divisor, times the quotient, 165, and if you add the remainder 1, you will get the dividend, 826. And that little character over there to the right, that's math bug. Checking the answer. How do we do this? Well, we could do 5, the divisor, times the quotient, 165. We could do it with tuples. 5 times 5 is 25. Start under the 5, the red 5. Then we do 5 times 6. Start under the 6. That's 30. And 5 times 1 is 5. Add them straight down. We got a 5, a 2, and an 8. If we add the remainder, we get 826, and that's the dividend. And we might want to stare at this below. We've got 5 times 165 plus 1 is 826. If you subtract 1 from 826, 1 is the remainder, you get 825. And 5 will go into 825 exactly. There will be no remainder, and it's 165 times. And that little guy to the right is math bug in another suit. Here we have another example of the new division method. We're going to divide 51 into 826,935. So we start off 51 into 82 one time. So 1 times 51 is 51. We subtract 51 from 82, you get 31. Now we slide over it to the 69. How many 51s go into 69? 1. And 1 times 51 is 51, so you see the other 51, and then we subtract, and that's 18. Does 51 go into 35? No. Bring the 35 down. So this is like a new dividend. Now we're going to go 51 into that number. Does 51 go into 31? No. Does 51 go into 311? Yes. Now these will be purple digits in the quotient. Now 6 times 51 is 306. And if we subtract, we get 5. We slide over to the 83. Does 51 go into 83? Yes, one time. That's in purple. We subtract 83, subtract 51, you get 32. 51 doesn't go into 5. Bring the 5 down. We start over, and these quotient digits will be in green. Does 51 go into 53? Yes, one time. And we subtract, we get 2. Doesn't go into 25. Bring the 25 down. 51 does not go into 22, but it goes into 225 4 times, and that's in red. And 4 times 51 is 204, and we subtract, we get 21. And that's how you do the new division method. What's the quotient? That's a tuple. So we bring all the numbers up, 1, 6, 2 ones, that's a 2, 1, and a 4. So 16,214, the remainder is 21. And we could ask now, make it a word problem. Suppose an auto dealership bought 51 cars for $826,935. And they say, what's the average price per car to the nearest dollar? Okay, we've got 51 into that number. It's 16,214, and the remainder is 21. Now 21 over 51 is less than a half, so we would say, okay, then the average price to the nearest dollar, we're not going to move the 4 up to a 5 because the remainder is less than half of 51, so it's $16,214. Rounding to the nearest tenth, we have 4 examples. Now the first one's 0.4567. We only look to the digit right next to the 4 to the right and no other digits. That digit is 5. If that digit is 5, 6, 7, 8, or 9, you move the 4 to a 5. If it's 0, 1, 2, 3, 4, we just keep it at 4. So our number rounded to the nearest tenth, it's in red to the right, is 0.5. Our next example, 9.34. Now 4, 3, 2, 1, 0 does not change the 3, so our rounded answer to the nearest tenth is 9.3. Now we have 8.1499, and the digit next to the 1 is a 4, so we don't change it. The 1, it's 8.1. Now some people say, well, wait a minute. The 9 next to the 4 would make that a 5, and then we'd have 0.15, and the 5 would make the 1 a 2. But that's not the rules in rounding. The number next to the 1 is a 4. You don't care about any other numbers to the right, and that's 8.1. The next example is 189.96. Now the number next to the 9 is a 6, so that means the 9's going up to a 10. Well, you don't write 10 after the decimal, so the 1 goes to the 189, that'd be 190, and dot 0. You use that 0 because it's to the nearest 10th. Round to the nearest hundredth. Our first number is 0.2699. The hundredth is the second decimal place. That's where the arrow is pointing. The number next to the 6 is a 9. The 6 goes to a 7, so the answer's in red, 0.27. And that's red, 27 hundredths. Okay, our next number is 14.3607. The number next to the 6 to the right is a 0. The 6 does not change. If it's 4, 3, 2, 1, or 0, it does not change. So the final answer is 14.36. How do you say it? It's 14 36 hundredths. Our next number, 9.8279. The number next to the 2 is a 7. That 7 makes the 2 go to a 3, so it's 9.83. We have a money problem. We have $6 and 0.239. The 9 makes the 3 go to a 4, so we have $6.24. Which decimal number is largest? We start from left to right, so we have zeros for all of them. Dot, each of them have a 6, 666. They're all the same. 110. That number, the third number, is thrown out. Doesn't matter what those other digits are. And now we have the choice between 0.615 and 6149. You might think the 9 makes the 4 a 5. Well, that's when you round. So the ones are the same. 5 is bigger than 4. So the top number, 0.615, is the largest. Write the mixed numbers as decimal numbers. This is easy. How do you say 5 and then 4 over 10? It's 5 and 4 tenths. The 4 is in the tenths, so the answer is in red, 5.4. That's 5 and 4 tenths. How do you do 5 and 34 hundredths? Well, the 34 is hundredths, so you start in the hundredths slot, and you come back, so it's 5.34. How about 5 and 7 25ths? Well, now 25 is not 100, but if we were to multiply both 7 and 25 by 4, you'd have 28 over 100. So we see our answer is 5 and 28 hundredths. The next one's kind of weird, 5 and 18 tenths. Well, you can't stick 18 in the tenths, but you could divide 10 into 18 and get 1.8. And then add that to 5, and that would be 6.8. Percents. Here we go. In percent, written as in and the percent sign. What does it mean? It means in parts out of 100. And that's equal to n over 100, the fraction. And we have this thing on the left, d, then sub 2p. This is how you change decimals to percents and percents to decimals. If you start with a decimal, you go to the right to get to p. You will move the decimal 2 places to get a percent. So we take our first example, 0.04. Move that decimal 2 places to the right. So 1, 2, that's 4 dot. It's an integer, so we don't put the dot. That's 4%. Now let's go the other way. We have 4%. How do you get the decimal? The decimal in 4 is after the 4, and you move it 2 places to the left, P2D, and that would be 0.04, and we put a 0 in front of our dot. So we can go back and forth from decimals and percents. Now let's take the decimal number 0.15. That's 15 hundredths. So you could almost immediately say, hey, that's 15%, but let's do it with moving the decimal. We move it 2 places to the right, 1, 2, that's 1, 5 dot. We don't write the dot after the 5, that's 15%. And if we take 15%, we're going to have the decimal after the 5. We go 2 places to the left, and that's 0.15. Now we got 0.2. You move it 2 places to the right. There's no number there to the right after 2. It's a 0, but nobody writes it, so it's 0.20, and you move it 2 places to the right. It's 20%. And if you put the dot after the 0 and move it to the left, that's 0.20. Nobody puts a 0, so it's just 0.2. Now we got 0.025, 2 places to the right, 2.5%, and go back and make it a decimal. You go 12.025 and a 0 in front of your dot. Now we have a very interesting one, 0.0025. We're going to make it a percent. You move it 2 places to the right. That's 0.25. Put a 0 in front of your dot. 0.25%. What is 0.25? As a fraction, it's 1/4. So 0.25% is 1/4%. That's not 25%. It's 1/4 of a percent. And if you were to say, okay, what's 1/4 of a percent as a decimal? You say, okay, 1/4 is 0.25. So it's 0.25%, and you move the decimal 2 places to the left, and you get 0.0025. So you got to be very careful. It's 2 places to the right to get a percent, and if you have a percent, it's 2 places to the left to get a decimal. And there's that little math bug again. Percent of a number means multiply. Percent times the number. Now, I got 9 problems. In the first, we're going to do 5%, 2.4%, 0.3%, 30%, 30%, 1.5%, 10%, 5%. You might look, I've moved the decimal 2 places to the left. So you'll see 0.05, 0.024, 0.024, 0.003 for 0.3%. 30%, move it 2 places over, just 0.3. Don't need to write the 0. 1.5%, 0.015. 10%, move it 2 places, 0.1. You don't need to write the 0. 5%, 0.05. By the way, the percent of a dollar is the cents of a dollar. So when you say 5%, you say, okay, in money, that's 5 cents. That's 0.05. Another way of remembering it. And then we're going to multiply these times certain numbers. So we'll start with the first one. 5 times 12 is 60. You got 2 digits to the right. So that would be 0.60. You don't need that extra 0, 0.6. 0.024 times 2 is 0.048. You have 3 digits to the right. Start on your right, come back 3 to the left. That is 0.048. 0.024 times 0.3. What's 3 times 24? 72. 0.243. There are the 4 digits to the right. Start on your right, come back left. That's 0.0072. You got 0.003 times 40. What's 3 times 40? 120. How many digits are to your right? 3. So 120. You come back 3. You got 0.120, but you don't need to write the 0. Just 0.12. Now we got 30% of 200. 0.3 times 200. Well, 3 times 200 is 600. 1 digit to your right, 60. And now we got 30% of 2. 3 times 2 is 6. You got 1 digit to your right, 0.6. And now we got 1.5% times 1.5. Well, you can do this. 15 times 15 is 225. And you count your digits up. 1, 2, 3, 4. 0, 1, 5, and the 1. Start on your right. Come back 4 digits to the left. That's 0.0225. And you got a 0 in front of our dot. Now we got 1%. That's 0.1. Don't need the 0 again. 1 times 285 is 285, and you got 1 digit to your right, and then the 85, that's 2 more, that's 3 altogether, so 285, you come back 3, that's 0.285. You might want to think about this. You do 1% of something, you move 10% of something, you go 1 place to the left. If it was 1%, it would be 2 places to the left. And you just slide the decimal left, an easy way of doing it. This is a money problem. 5% of $12.50. So let's say your tax is 5%. And you go in and buy something for $12.50. What's your tax? Okay, so what we got to do is 0.05 times 1250. And if you're going to try to do this mentally, 5 times 12 is 60. 5 times 50 is 250. That'd be 625. But we got an extra 0. So it'd be 6,250. How many digits do we have? So we got 6,250 mentally. We got 1, 2, 3, 4. So 0, 5, and a 5, 0. So 6,250, and you come back, and your tax is 0.625. So 5% of 1250. And let's see if we can see, is that reasonable? 62.5 cents tax. What's 10% of 1250? That'd be 1.25. 5% would be half of that, and that is 0.625. And if we're doing money, the 62.5 cents would round off to 63 cents. Changing fractions into percents. 5 is what percent of 20? What's 5 out of 20? Now 5 goes into 20 4 times, so that's a fourth. And a fourth of a dollar is 25%, which is 25%. Or we could say 5 times 20, 5 times 5 is 25 out of 100. Parts out of 100 is the percent, so that's 25%. 5 over 25. Well, we could do the top and the bottom, numerator and denominator, by 5. We would get 20 parts out of 100. That's 20%, but we want to remember that 5 over 25, 5 goes into 25 5 times, so 20% is also 1/5. Now we got 50 out of 2,000. We could knock out a 0, that's 5 parts out of 200, but percent is parts out of 100. So we could divide numerator and denominator by 2, so that's 2.5 out of 100, so that's 2.5%. Okay, our next one is easy. It's 2 parts out of 100. That is 2%. 7 out of 28. Well, 7 goes into 28 4 times. That's a fourth. So you just say to yourself, a fourth of a dollar is 25%. And it's because it's a fourth of a dollar is 25 cents, which is 25%. And 10 is what percent of 5? The 10 is bigger than the 5. So it's 10 over 5 is 2. And we go back to our definition of percent. In percent is in parts out of 100. You got 100 parts out of 100. That's 100%. But 100 over 100 is 1. So 1 is 100%. 2 is 200%. 3 is 300%, and so forth. Okay, now we got 2.3 over 4.6. 2 times 2.3 is 4.6. So we could divide the top and the bottom by 2.3, and we get a half. And a half is 50%. And they got 9 over 45. 9 goes into 45 5 times. That's 1/5. And that was like the other problem above. So a fifth is 20%. By the way, 2/5 would be 40%. 3/5 would be 60%. 4/5 would be 80%. So that's an easy way to do them with fractions. And 45 over 9 is 5. And just like the two above, 5 is 500%. Which class is better? Now we'll come to a typical problem in everyday life and how things get messed up. Now we have a class scores an average of 20 on a mathematics SOL test a year ago. 20 is not very good. This year, the class had an average of 30, and everybody was just going crazy. Oh, my goodness, what a smart group. And the question is, what was the percent increase? Percent increase is defined as new minus old divided by old. The old number is 20. The new number is 30. So 30 minus 20 is 10 over 20. That's a half. Wow. The group increased their knowledge by 50%. And then they had another class. They had an average of 90, and the top score is 100 on a mathematics SOL test a year ago. And this year, they only had an average of 91. My goodness, what was the percent increase? Well, we got 91 minus 90 over 90. That's 1 out of 90. And if you work it out, 1 over 90 is 1.1%. And so in this particular school system, they made raises dependent upon the percent increase in SOL scores. So the people who had the classes that were scoring 20 and got up to 30 got a huge increase, while the poor folks who had an average of 90, who were doing fantastic work with the students, went up to a 91, they didn't get much of an increase. Well, now that's how people mess up with percents. They think that just because the percent is higher, then that means that's better. But in fact, the class that's at 91 is a heck of a lot better than the class at 30. So even some adults might want to watch this video and rethink how you assign raises based on percent increase in knowledge. Here's another example about the percent of what number will give you so much dollars. So we're going to do a new tax on super efficient cars. And this particular state has decided that 4% will be the tax rate, and 4% of what number will yield $1 billion. So the state wants to increase its highway fund by $1 billion. So 4% times some number is 1 billion. So if we divide both sides by 4%, n is a billion over 4%, that's a billion over 0.04. And if you do your division, you move your decimal over 2 places to divide by 4, 2 places in the numerator, you will get $25 billion. So the additional car tax for these super efficient cars is $25 billion. Now let's say the price of a super efficient car is $50,000. Well, now 4%, that's the tax they're going to charge you. If you have a super efficient car, 4% of $50,000 is $2,000. And that doesn't seem too outrageous. You got to realize that these people are not going to the gas pump very much. So they rarely go to the gas pump. These are super efficient cars. So for a gallon of gas, they might get 100 miles per gallon. So they don't pay much tax with the gasoline. So the state figures, well, they got to pay us somehow. Well, what's the number of super efficient cars? We got $25 billion. How many 50,000s go into $25 billion? That's 500,000 cars. So that's not so wacky when you say 500,000 cars is not that many. If you got, say, 2 million drivers and the nation is pushing for super efficient cars and they get reductions at the dealership and they figure, well, this is a good deal. I only have to go to the gas station like once every 2 months. People say, yeah, that's good. I'll save a lot of money in gas, but then there's a lot of state tax that's not being earned from the sale of gasoline. So this is a way that a state could make up for that. So this is just an example, but the numbers get kind of large. Some people think, gee, $1 billion in additional revenue, but it would only take 500,000 cars to do this.